So in the previous lecture, we were talking about manifold suboptimization method. And we had gone back 100 years or so, and we were in the middle of World War II, and we were talking about the fact that we need to optimize the movement of troops and the movement of supplies. And the problem is, and you came up with a problem, and the problem is that I want to minimize f of x such that ax is less than equal to b. Okay. And the problem is that you cannot do projection onto this set. Projection is very difficult. And we cannot use conditional gradient method because that requires us to be able to solve a linear program of this type, and we don't quite know how to solve the linear program of this type either. Okay, so we cannot use any of the methods we have talked so far because I don't know how to solve this particular problem. And I wanted to remind you, what does this set look like? So it basically looks something like either an enclosed convex set, something like this, right? So this particular set is going to look something like this, or it could look something like this, going all the way to infinity. Okay, going all the way to infinity. So it's going to look something like this. So I'm sure you guys have thought about it in the last 2 days. So I want to collect some ideas about how you want to go ahead and solve problems of this type. So what have we learned so far? Projecting onto the surface or line, easy part. Okay, so we looked at it in the previous lecture, and we saw that projecting onto a surface, onto a plane, a hyperplane, is very easy, but projecting onto this solid body is very difficult. So how would you go about solving this problem? Yeah.
I was thinking about approximating all the hyperplanes and constrain them on the hyperplane.
Constrain them on the hyperplane?
Yeah. Just
okay. 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 Good. Any other ideas? Any other thoughts? So that's somewhat right. What we want to do is do gradient descent on the hyperplanes until something happens, and then we figure out what to do when something happens. Okay, so this is the idea. Let's say I started from this particular point. I'm going to do gradient descent along this hyperplane. Okay. Now I have reached this particular line. I'm going to do gradient descent along this line. Now I have reached this particular point, and I need to figure out whether I want to descend along this direction, descend along this direction, or descend along this direction. So let's say the algorithm told me that I need to start descending along this direction. So I'll start descending along this direction. And then I'll reach my x star by just constraining myself to go along the surface unless my algorithm tells me that I need to go inside the set. What this leads to is an algorithm where projection is very easy to do at every time step. And when the algorithm tells me that I need to go inside the set, then I don't have to do any projection because I'm inside the set, right? And when you are inside the set, there is no projection to be done. You can just move along in any direction. Okay, so that's why it's called manifold suboptimization. So what's a manifold? Manifold is a surface, it's a hyperplane, it could be a curved plane. So in this case, the manifold is referring to this hyperplane that we are constraining ourselves to. And so manifold suboptimization means that at every iteration, I'm going to look at a manifold and I'm going to optimize within that manifold. Okay, and once I get to a point where I have to pick a choice, I can go in this direction or I can go in this direction, then I will solve some other optimization method and figure out where exactly should I be moving towards. Okay, so I'm inside the set, I can move around in any direction, but once I reach this corner, I can only move along the corner direction. Okay, unless the algorithm tells me that I need to move inside the set. So that's the manifold suboptimization method. I want to introduce some terms. First thing is set of active constraints. Okay, I first need to tell you what this matrix A looks like. So I'm going to write the matrix A as A1 transpose, A2 transpose, AM transpose. Okay, B is B1 to BM. So M is the number of rows in A. Remember, this is a vector in Rn. And remember that X is in Rn. These are all scalars. B1 is a scalar, B2 is a scalar, all the way up to Bm is a scalar. Okay, any questions on this matrix A and B? Hopefully not. So what is a set of active constraints? J such that Aj transpose X equals to Bj. Okay, so going back to this, let's go back to this set. So I have surface 1, 2, 3. There is a fourth one on the other side and fifth one in the other side. And let's say there is sixth on this side. Okay, so I have 6 different hyperplanes, 6 different constraints. So I have A1 to A6, and this is R3. Okay, so my N equals to 3 and M equals to 6. Each of the surface is given by A1 transpose. So this is A1 transpose X equals to B1. That's this surface, surface 1, and then A2 transpose X equals to B2, that's surface 2, and so on and so forth. And remember, I have this inequality here. So by inequality, what I mean is the surface is included and everything below the surface is included. And because you have 6 constraints, you ultimately get this solid tunnel, and that solid tunnel is my constraint set. Let's look at some points. So I'm here, x1. What are the set of active constraints here, and what are the set of inactive constraints? So which constraint is active if I'm standing on surface 1? It's this constraint, A1 transpose X equals to B1. So at x1, so A of x1 is equal to 1. What about this point, x2? What is A of x2? Which constraints are active at x2? 1, 2, and 3, perfect. So remember at x2, it's at the intersection of surface 1, surface 2, and surface 3. So I have 3 different active constraints. What about x3? What is A of x3? Which all constraints are active at x3? It's 1, 2, and 6. Okay. Okay, so at least by looking at the picture now, okay, let's pick another point. X4. What are the set of active constraints at x4? 1 and 4. Okay. Hopefully by now you are very well trained on figuring out what the active constraints are by looking at the picture. Mathematically, we write it as this particular form. And I'm going to make a strong assumption. Assumption is at every point x, aj such that j is in ax are linearly independent. Okay, so there are situations, you can construct situations where these AJs are not linearly independent. One example is if you have equality constraints. So you have inequality constraints and you have equality constraint. What do you do when you have equality constraint? Remember in assignment 1, you did elimination of a variable because you had equality constraint, you can eliminate one of the variables, right? So what you do is whenever you have equality constraints here, you eliminate those variables in order to get a constraint of this particular form, and then this condition would be satisfied. Oh, I mean, I hope the condition would be satisfied. You could also have redundant constraints. So one situation where this wouldn't be possible. So suppose you have x1 less than equal to 5 and x1 less than equal to 7. Which constraint is redundant? 7. Okay, so this constraint is redundant. So you will have to algorithmically figure out which constraints are redundant and you will have to remove those constraints. Okay, just yeah, so that's something, it's a complicated process to remove all the redundant constraints so that this assumption is going to get satisfied. Remember, when you are, let's say you went to MathWorks and you're working for MATLAB, you're building the next version of optimization solvers for MATLAB. If a user is giving you an input, which is an optimization problem, it's your job to figure out which of them are redundant constraints and remove those redundant constraints, because users will never know what the redundant constraints are. So I could potentially give you a problem statement in MATLAB. I can give this problem statement to solve. So x1 greater than equal to 0, x1 less than equal to 5, x2 greater than equal to 0, x2 less than equal to 5, x1 plus x2 less than equal to 100. I can give this problem to MATLAB. And then it becomes your job to remove the redundant constraint. What's the redundant constraint here? x1 plus x2 less than 100. That's a redundant constraint. So you need to remove this constraint. So that's your job. We won't study how to remove redundant constraint. but we'll assume that there are no such redundant constraints in the problem statement. So we'll assume that the set of active constraints, you look at those AJs, they are linearly independent in Rn. Remember, AJs are Rn dimensional vectors. So these are Rn dimensional vectors. So that's my assumption, okay, throughout the process. The other question I want to touch upon is, let's say I'm standing at a point X and I want to figure out what are the set of feasible directions at X. Okay, so I'm standing at X1 and I'm looking at all the feasible directions that are feasible at X1. Then what exactly is this direction supposed to satisfy? So let me.
X1 on the surface or?
X1 is on the surface. It's on the surface 1. Okay, but remember at X1 I can go inside as well. Okay, so that's also a feasible direction. I'll still remain within the set. So what are the set of feasible directions? So let me define a matrix A. I want to use, let's write AX, which is the set of AJ transpose. J is in the set of active constraints. So I'm going to stack all the AJ transpose one after another, and I create a matrix, and the set of feasible directions is AXD less than equal to 0. I'm going to replace AX with AK because I'll be at the kth step, so where X will get replaced with XK. So I'm just writing it in a weird fashion right now, but we'll make it concrete in a bit.
AX is the one that we have after removing the redundance.
Yes, so this you always have to remove all the redundant constraints and then get the problem in this format, and only then you start solving it. Okay, so what's the algorithm? The algorithm is I'm starting from X0 and I'm going to move in the direction where I'm going to be constrained to AX D equals to 0, and I'm only going to take a step in that direction. Okay, when I cannot take any step in that direction, when my D star turns out to be equal to 0, then I'll figure out where exactly I have to go. So this is how the algorithm will proceed. I want to minimize at every point of time. Well, okay. Xk plus 1 equals to Xk plus alpha k dk. Alpha k will be picked according to the minimization rule, so we'll not talk about alpha k. We need to figure out what dk is going to be. So dk should be argmin of d in Rn and there will be two cases. Case 1, the easy case, dk is not equal to 0, and case 2, A dk equals to 0, in which case drop a constraint, and case B, dk equals to 0 and xk is stationary. Okay, everyone has written it down. So let's think about it. So I'm standing at xk. These are the set of feasible directions. But remember that it's very difficult to project onto this set. So I'm not going to project onto this set. I'm going to project onto this set, the one with equality constraint. And then I know that solving this particular problem is comparatively easier. I can actually solve it. I'm going to write the solution by hand. But let's think about this particular problem for a bit. So d equals to 0 is a feasible point in the set, because if I pick d equals to 0, it satisfies this particular condition. So if I solve this particular optimization problem, I could have a situation where dk is non-zero or dk is 0. If dk is non-zero, I can start descending in that particular direction. If dk is equal to 0, then it means that I have too many constraints. So AK is a full rank matrix. I have too many constraints. I need to drop a constraint and start descending within the set. So I need to drop a constraint. Alternatively, I could have dk equals to 0, but that dk is equal to 0, there is no way for me to descend because xk is a stationary point within that set. So it satisfies the necessary condition for optimality, and then I can hopefully use some sort of sufficient condition to ascertain that the point xk is indeed an optimal point. Okay. So in particular, if f is convex, then I know that a stationary point is an optimal point. If f is non-convex, then all bets are off. Okay, I don't know whether stationary point is good enough or not, but hopefully it has good performance in practice. Okay, so how do I know what the value of dk is? So the way to solve this particular problem is using, we talked about it a bit in the previous lecture, but I'll just write down the solution. We will know how to solve this class of problems in the subsequent classes when we talk about Lagrange multiplier theory. So right now I'll just write the solution. This is hk inverse gradient fxk plus ak transpose mu, and mu equals to minus ak hk inverse ak transpose So I compute an intermediate variable mu based on the matrices that are provided to me, and then I compute the direction dk.
HK is evaluated.
So hk could be either the second derivative of the function, or it could be just identity matrix, or it could be some approximation of the second derivative of function, or it could be some positive definite matrix that you experience that has good performance for this particular problem statement that you're solving. Okay, all I require is hk to be positive definite. But naturally, if you pick second derivative, then you have the best performance. Okay, so let's look at these two cases separately. So what happens when dk is not equal to 0? So if this particular quantity is not equal to 0, so remember I mentioned that d equals to 0 is a feasible point in the set. So ak times 0 is equal to 0, so it satisfies this condition. So what I know is, so I'm looking at this case here. So gradient fxk transpose dk plus half dk transpose hk dk is less than equal to gradient fxk transpose 0 plus half 0 transpose hk 0. Why is it less than equal to? Because 0 is a feasible point in the space. So if I pick d equals to 0 and dk is the optimal solution to that problem, so definitely the function value should be less than equal to the function value at 0, right? That's obvious. Okay, everyone clear why this should be the case? Okay, so this is the objective function. I'm optimizing the objective function. So the optimized dk must have a value lower than equal to the function value at some point in the space. That's a feasible point. This value is equal to 0. So therefore, gradient fxk transpose dk is less than equal to minus half dk transpose hk dk, which is strictly less than 0. In other words, dk is a descent direction. Okay, our goal forever in optimization is to pick a direction where the gradient with respect to the function, gradient of function transpose the descent direction is always negative. If it is negative, then I know that I'm moving in the right direction. I'm moving in a direction where the value of the function is decreasing. And it turns out that if I pick dk according to this fashion, it seems to be satisfying that condition as long as dk is non-zero. So if dk is non-zero, dk is a descent direction because it satisfies this inequality, strict inequality. Remember, this is not less than equal to 0. This is strictly less than 0. So I am indeed improving the value of the function at the new point xk plus 1. Any questions so far? Yes.
Can you clarify why you put when you define that inequality, you put the zeros?
Yes. So d equals to 0 is a feasible point in the set. I'm minimizing a specific function of d, right? So if dk is the optimal solution, then the function value must be less than equal to the function value at any other feasible point in the set. In particular, it will be true for d equals to 0. Okay. Any other question? Okay. So if dk was non-zero, if I solve this problem, dk is non-zero, then I know that it's a valid descent direction, and therefore I can take a step in the direction of dk by picking alpha k according to minimization rule or line minimization rule or whatever. Wonderful. Now let's get to the case of 2a where dk is equal to 0. So I solve this problem and it turns out that this vector is equal to 0. Then what happens? So I'm going to look at this particular case now where dk is equal to 0. So dk equals to 0 implies that gradient fxk plus ak transpose mu is equal to 0 because hk is a positive definite matrix. So I can multiply it by hk on both sides and I get this particular conclusion. This implies gradient of fxk equals to summation mu j aj. J is in axk with a negative sign. Okay, so let me draw a picture. So I have two okay. I'll erase this side of the board. Okay, I want to spend some time on this particular constraint. So remember, we need to drop a constraint. So we need to drop one of the j's here. And I want you to think about what j should we drop so that the next step is going to be a descent step. Okay, so I am standing at this particular line. This is my xk. And there is a vector. There is a vector like this, and there is a vector like this. This is, let's say, a1, this is a4. So I have two active constraints here. And it turns out that the gradient of the function is pointing in some other direction, which is a linear combination of a1 and a4. So a1 and a4 are the two gradients of the hyperplanes, and it's pointing in these directions. And now the gradient of f is pointing in the not necessarily in the direction of a1 and a4, but it's a linear combination of a1 and a4. And now I need to remove one of the constraints because otherwise I'm not getting the descent direction. Okay, so going back to 1944 or 1942, the direction that you want to drop is for the case where mu j is less than 0. So the claim is drop j bar such that mu j bar is less than 0. So I have j in axk, I have j equals to 1 or 4. I'll look at mu1 and I'll look at mu4. And I'm going to, let's say mu4 is negative. I'm going to remove 4 from the set of active direction and resolve this problem without that particular constraint. Okay, so I'm going to drop one of the constraints and I'm going to then solve the problem all over again. Okay, so let's say after I drop j bar, I'm going to define this matrix ak bar equals to aj transpose j in a xk minus j bar. So I've reconstructed this matrix AK and I've removed one of the rows, the j bar row of AK completely. Okay. It turns out that if you are able to find a mu j bar less than 0 and you drop that constraint, then the updated d bar k d bar k satisfies gradient fxk transpose d bar k is less than 0. It requires a bit of computation. The computation is given in the book. We won't go through it in the class, but the idea is very similar to what we did in the previous case, where you proved that the gradient of fxk transpose d bar k would become strictly less than 0. And so then d bar k is your descent direction. So that's the case 2a part, and then case 2b. All mu j's are non-negative for all j that are active at xk. In this case, what I have is gradient of fxk transpose d equals to minus summation mu j aj transpose d, j is in axk, and I want to remind you that what are the feasible directions? All feasible directions, not just the ones that are constraining to the manifold, but all feasible directions that are also going inside the set. Those directions, feasible directions, satisfy I want to write it somewhere. So a few minutes ago, we said that all feasible directions would satisfy axk d less than equal to 0, which is the same as saying aj transpose d is less than equal to 0 for all j in a xk. Right? So we talked about this just a few minutes back at the beginning of the class. So it means that for all j that are active, aj transpose d would be less than equal to 0. So this is positive or non-negative. So mu j's are non-negative. aj transpose d is non-positive. I have a negative sign here. So this is positive. This is negative. I have a negative sign. So this is non-negative. And what does it say? That the derivative of the function transpose all possible feasible direction is non-negative, which implies that xk is stationary. Or in other words, it satisfies the first order necessary condition for optimality. And this is the famous algorithm that people developed, researchers developed back in 1940s for the purpose of optimizing the movement of troops and stuff during the World War II. I'm not sure whether it was actually implemented or not, but it was definitely developed with that intention. when the function f is, so it was actually developed for the case where f of x is a linear function. So it was developed for f of x equals to c transpose x. It's called a linear program, and the name of this algorithm was simplex algorithm. So this was the algorithm that they called back at that particular point of time in 1940s and 50s. But then people generalized this particular algorithm for solving nonlinear optimization problems, and they gave it a name, manifold suboptimization method. So a lot of cool algorithms were developed for war purposes, just so you know. Okay, so a lot of the stuff that we are doing was developed for rockets, for missiles, for dogfights, for moving troops in the World War II, and for Cold War. Okay, so a lot of people have died for us to have this course in 1920s. No, sorry, 2020s. Okay, but this is important stuff because we need to know the history, right? So why did people develop these algorithms? So, anyways, let me remind you what we did. So we had this minimizing the function over a set ax less than equal to b. I cannot solve that problem because that's too difficult. I cannot do projection onto that set. So I said, look, I'm not going to do the projection over akd less than equal to 0. Let's just do projection over akd equals to 0. Okay, so I'm just going to constrain myself to move along a manifold until somebody tells me that I cannot move along the manifold because it's not a descent direction. It's not a valid descent direction. So I solved this particular problem, and then suppose dk was not equal to 0. Then we proved that, okay, it's a valid descent direction because it makes negative inner product with the gradient. So that's good. Now suppose dk equals to 0, then I need to drop a constraint, and we came up with a method to drop a constraint. So I'm going to drop the constraint for which the corresponding mu j is strictly negative. Then we said that d bar k, like once you solve this updated optimization problem where you've removed one of the constraint, it turns out that then d bar k is strictly a descent direction. It's a valid descent direction. If you have two such mu j's, if you have two mu j's that are negative, you just pick one of them and you drop it. Okay, so let's say constraint 1, 2, and 5. 1 and 2 has negative mu. You just drop one. Okay, you don't drop both of them, just drop one of them. So you dropped one of them and then you proceeded and you got this result. So d bar k becomes a valid descent direction. Then I'm going to pick alpha k according to minimization rule, and I'm going to transition to xk plus 1. Alternatively, I looked at my mu j's and I realized that all of them are non-negative. Okay, so there is no descent direction that I can, there's no constraint that I can drop. And then we ended up proving that actually in that particular case where all mu j's are non-negative, xk is actually a stationary point, and therefore we are potentially standing at the optimal solution already. And I don't need to move around because I'm at a locally optimal solution. So that's roughly in a nutshell what manifold suboptimization method is. And it gives you an idea of how do you solve problems where you hit a situation where you are not able to solve the problem, you convert it into a simpler problem that you can solve, and then proceed, come up with a structured way of solving that particular problem. And we'll see more evidence of this in the subsequent classes where we will use these kind of ideas to solve optimization problems. Okay, any questions so far on manifold suboptimization method? I want to talk about another important method, which is called mirror descent. Okay, the idea in the mirror descent. Okay, so I think it's important to know what we are trying to do. Okay, so let me go back to the original discussion about the second derivative business. Okay, so I said that f of x plus d is roughly equal to f of x plus gradient fx transpose d plus half d transpose second derivative of the function times d. So this is my Taylor series approximation, right? This is something that that we have all studied in the calculus class. And if I want to find a descent direction, I can try to minimize this function, and I can get d star, which is a descent direction, by doing second derivative inverse times the gradient of f. So what mirror descent says is that the purpose of this term, what is the purpose of this particular term? It's to approximate the function around x. Okay, come up with a better approximation of the function around x. So let's do the following. Let's replace it with some other function, some other approximation. Let me call it x plus d times x. I mean, not times, but this is a semicolon. I mean, this is just, think of it as a comma. Okay, so I'm taking this function d takes in two arguments. Okay, x plus d and x. So I'm going to say that my f of x plus d is roughly equal to f of x plus second derivative of fx transpose d plus this term, which hopefully should be convex in d, convex in x plus d. So I maintain, remember, this term was supposed to be convex. If the second derivative is positive definite, it's a convex term. So I'm going to replace that convex term with some other convex function, okay, which is convex in x plus d. And now I'm going to find the descent direction d by solving this particular optimization problem. And that's studied under the umbrella of mirror descent method. So instead of picking the convex function that comes out of Taylor series, you are going to replace it with some other convex function. And hopefully solving this particular problem is much easier than solving this particular problem. Okay, so the
graph is not convex, or we are trying to find a convex approximation.
It's not really a convex approximation. It's just a convex function that better approximates the function. You don't need to have a bound on how well it approximates the function, but it makes your computation much easier. Okay, so the idea here is that you will pick xk plus 1 equals to xk plus alpha k x bar k minus xk, and x bar k equals to arg min of x in capital X gradient fxk transpose x minus xk plus the divergence of x xk. And this is known as a mirror descent method. And the reason why mirror descent is important, and we'll not go very deep into this, but I'll give you an assignment problem where what you will see is sometimes if you are solving this particular problem, it becomes much easier to solve this problem over the convex set, and you don't have to do any projection business. Okay, all of that is useless in those cases. So you can solve this problem, and you can get x bar k is computed with minimal computational resources. Uh, Whether you want to use mirror descent or not is more of an art than science. Okay, so you will have to identify a divergence d, a function d which is strictly convex in x, so that solving this optimization problem over the convex set capital X is very easy. Okay, I'm not saying that it's easy. In general cases, it's more of an art, and you will have to investigate a lot of time. Like people spend half of their PhD or maybe an entire year identifying the right divergence so that solving this particular problem is very easy for a specific context. So you are a wireless systems guy, you want to route the packets in a wireless systems. How do you pick the divergence D so that the resulting algorithm actually satisfies all the requirements for routing the packets in a wireless systems? There are definitely a class of divergences that people have used extensively in the past, and therefore you can get your inspiration for solving your problem from those divergences. But in general, if you are exposed to a new problem, you will have to spend considerable time and effort in identifying a convex function that allows you to solve this particular problem with minimal computational resources. I just wanted to add this because it's a beneficial algorithm, specifically if you are solving problem on devices that do not have a lot of computational power. So in those cases, this algorithm turns out to be easy to implement, but in general, identifying the divergence is a very difficult problem. So just keep that in mind. So that's studied under the umbrella of mirror descent. There are also other algorithms like proximal algorithms that we won't be talking about in the class, but there's a whole bunch of algorithms that are used for solving optimization problems over convex sets. And what we have studied in the class are the simpler algorithms that doesn't require a lot of mathematical machinery. Wonderful. So I'll see you guys on Monday now. On Monday, we'll start a new topic called Lagrange multiplier theory, and we'll talk about Lagrange multiplier theorem, which is used to solve general constraint optimization problems. So see you on Monday. Have a great weekend.